Thank you all for coming. Very excited about this one. So this is the second installment of our Complexity Speaker Series. Today we have Professor Douglas Guilbeault, who's at the Stanford School of Business. And I actually think I'm just going to cut it off there because it's got a lot of stuff to get to and I'm really excited.
Okay, awesome. Thanks so much for having me here today. I've long been a fan of this institute, and it's a special privilege to share with you some of the recent stuff I've been working on regarding networks. And at least for a social science talk, this is going to be very theoretical, but I think for all of you, this is much more resonant with the kind of work you do. So this is a special treat to be able to share this with you. So when you're talking about social contagion, a particular family of social contagion models, and what I hope to communicate to you today is how a simple reframing of certain concepts that have been around for like over a couple decades actually seem to unlock a variety of unexpected dynamics and insights that might, I hope, actually have some generality, not just across the models I'll show you, but it actually supports some new questions for thinking about developing like a kind of social theory for something like cultural evolution. So I'm going to talk about by intro because it builds off a body of work. Some of you may be familiar with this. It builds on this distinction between simple and complex contagions and is particularly building off a sort of formalism that I developed with my advisor at the time, Damon Santola, for this construct of complex paths. So even though that's from a previous paper, it's important to be able to communicate that because what I'll then be talking to you about is a property of complex paths, which we didn't realize at the time, but in some ongoing work with my postdoc, Fabian Chofenig, we have uncovered what seems to be a pretty fundamental property of complex paths that has a variety of implications, especially for a number of canonical intuitions regarding the role that network theory plays in social behavior. So we'll get into some theoretical and empirical results, and then with some time, I hope to be able to share with you some of the new stuff we're exploring regarding this question of diffusion controllability or contagion controllability, because I think new engineering capabilities actually become possible once we have this construct of directedness in mind. Okay, so getting into simple and complex contagions, so it's going to be a little bit of a whirlwind because it's a long-standing literature, last 20 years or so. But basically, I just want to start by saying there's been this established way of thinking, at least in early attempts to import epidemiological models into culturally relevant human behavior, which you've no doubt encountered through the popular term of virality, things going viral. But the important thing to realize is for many, this actually just isn't a poetic metaphor that's stylistically compelling. You have people like Malcolm Gladwell who really popularized this narrative by saying this is not an analogy in the poetic sense, it's a literal analogy. Ideas can be contagious in exactly the same way that a virus is. The problem is when you really start trying to use the formalisms which assume traditional definitions of contagiousness to talk about social cultural phenomenon, many of the core assumptions you need to make actually break down. And that's where we start introducing this distinction between simple and complex contagion. So one of the basic assumptions that gets simple contagions off the ground is that by and large, single exposures are sufficient for inducing an infection of sorts. So we can think of something like a pandemic where someone sneezing on you is sufficient. And so in this case, of course, we can get really rapid forms of spreading. And this is why things like long ties that cut across social space, like someone getting a flight from one country to the other, are so destabilizing in the context of a pandemic because that is sufficient for triggering cascades in the new place that they go to. Now, what I want to do is zoom out because, of course, there's many different models and people have added bells and whistles here and there, which make this a little bit more complicated. But what I want to point out to you is actually that notion of simple contagion went hand in hand with some of the initial definitions of path length in networks to the point where, at least in their use in social theory, they were synonymous. And so what do I mean by that? If we think about early constructs like the 6 degrees of separation, the way that that construct was defined and introduced was through a form of diffusion experiment. So you had Milgram, who showed if I'm trying to get a package from some seed person through only pairwise interactions to get to some target, tends to have 6 steps in the network, right? And what that path was then used was to define a characteristic measure for networks of path length. And no doubt many of you have then seen the explosion of research that has since come, and is in some ways the foundations of network theory and computational social science, which was to generalize this in a formal model of small world networks, where what you're doing is through a form of randomness, basically creating more opportunities for these ties that connect to someone in some different part of the social space. And of course, the anecdote there as a sort of poetic moment is like the reason why we call it a small world is because you go to some party, you think it's all new people, and lo and behold, one of your oldest friends there, or you meet someone and they actually know someone who's really close to. So it evokes a sense of serendipity, which is related to that kind of randomness factor, right? Now, what was key to this is then us literature and sociology, Granovetter, as I'm sure many of you know, the strength of weak ties was to really think about the social consequences that these random ties that cut across places have. In particular, what this connected to in the context of 6 degrees of separation was the surprising result that through these these ties that cut across social space, everyone's much closer than we realize, right? So did you know that you're only a few steps away from Obama and that kind of thing? And the strength of weak ties is that actually many ways people get exposed to consequential opportunities, the connections that they form, the information that they receive that's impactful in their lives comes through these long ties. So a lot of stock was put in that as an engine for social dynamics. And in many ways, that was continues to be a very valuable mode of analysis for thinking about how networks mediate social and cultural phenomena like personal opportunities and so forth. The challenge is when we start thinking about complex contagions, all it is a simple shift of that basic assumption where is a single exposure enough, right? And what we start to ask is like, what if there's a phenomenon where you need a certain amount of peer reinforcement? You can think about it in common terms like peer pressure. But it's not simply because one way to think about it is, oh, there's some sort of function. And the more that I'm exposed to somebody else, it just increases the likelihood that I'm going to adopt a certain thing. Maybe it's a controversial belief that initially you're skeptical. So that has something to do with what we're talking about here. But it generalizes more to phenomenon also like norms, where what we mean by norm is that it is actually a collective phenomenon. You do it because you think most other people do it. And there's evidence in your experience that most other people do it. Maybe it's dressing formally at funerals or these sorts of things, other forms of norms where following it and avoiding some sort of social punishment has to do with belonging or fitting into some sort of group level behavioral trait. And so what we see in a complex contagion and the way that we typically model this is a diffusion process where agents will only adopt particular behavior when they've been exposed to a sufficient amount of people in their local neighborhood. Now, as a formalism, we tend to simplify this through some sort of threshold dynamic. So in this case, you could say, oh, maybe this person needed to see 3 people, or you can think about it as a fraction. So they needed 50% of their local neighborhood. One thing I could go into greater detail, but I just want to frame right now that this threshold is just a convenient implementation to induce a certain set of dynamics. It is not synonymous with complex contagion theory. Actually, many different models, many of which do not actually rely on thresholds, can induce complex contagions. It's like weighted belief networks where there's just continuous functions and constraints can induce complex contagion dynamics. And so in many ways, what complex contagion dynamics come down to is that there's a certain amount of repeat exposure in some clustered sense that is required to induce the spreading process. And so when we think about the network mechanisms that are required to support the spread of complex contagions, we start thinking in terms of what we call bridges, which is sort of sustained shared connectivity that can lock in these repeat exposures. And there are many, in terms of a social dynamic, many factors that cause contagions, why you would expect it to have more complex rather than simple dynamics. I won't go into all these details. It's just to say that in its spirit, it's actually trying to be a social theory. So it's less about the mathematical formalisms. It's more about thinking through factors like the following. So complementarity is various forms of behavior or technologies that are only useful if a critical mass of other people are using them. So you wouldn't have adopted Facebook if you didn't know anybody on Facebook. And so things like Facebook have been shown to spread like complex contagions. Legitimacy is maybe you're doubtful that a given behavior is socially valuable. Maybe it's perceived as risky. And so things like support for the gay pride movement, adopting some political symbol that indicates support with that, you face possible risks of sanctioning. Other people in your social network might disagree. So there's a sort of strength in numbers when you see a certain number of people in your life doing this, you know that you will have their support by participating in it. So there's various social factors, I won't go into all the details, that are different that basically create conditions under which you would need a certain critical mass of people in your network to lock in this behavior change. So what I'm going to get to now is the network theory, because this paper that I published in 2021 with my advisor basically points out that as soon as you make that simple shift where you need exposure to multiple different people, again, it could be various numbers, various amounts of fractions, so long as you're in some sort of reinforcement regime across people, it actually can give you a very different picture of the network structures that matter for diffusion. And like I said before, in the case of simple contagion, that was a way of operationalizing a sense of social distance. And that's when a long tie could cross social space. Suddenly something could jump right across and accelerate its spread. But what we tend to see is things like that are actually unable to spread complex contagions under a variety of conditions. And the broader implication being that the sense of social distance, the proximity we get between people, the ability for stuff to spread between them, is not adequately captured by the traditional network measures that we have. In fact, people can look close together in a network sense through simple contagion and yet be totally unable to spread complex contagions between them. And so what we did was formalize a notion of path structure that captures the kinds of structures that can spread complex contagions, and then develop a measure of social distance from that. And so what we get is this measure of locally sufficient bridges. I won't get into all the formalisms, but to give you a really painfully trivial example, if the threshold is 2, we're going to say, okay, a node like that can be activated. We're going to call that a socially sufficient bridge. Whereas this really obvious case, okay, this person is only connected through 1. If there is a certain amount of reinforcement required, just complex contagions can't get to that person. So what we develop is a way of capturing all different kinds of motifs through which these bridge structures emerge, and then can iterate over a network under various different assumptions of peer reinforcement and ask whether the local connectivity forms a bridge where there's going to be enough reinforcement through an exposure. The idea I want to communicate now is that you really do get different paths that emerge. So if we think about I and Q here, what we would typically do, say, if you're thinking of something like betweenness centrality or other indicators, you like, what is the shortest possible path, the geodesic on the graph between those nodes? And that's what this blue line is highlighting here. But if you're asking, what is the shortest possible path through which a complex contagion could travel from I to Q, it can't traverse that path. It has to go a different way. Now, that's just a starting point, so that paper looks into how it impacts the measure of distance here, and that has all kinds of complications. But it's to say that actually you can, in some sense, coarse grain a network into the complex contagion architecture and you can get community structure out of that. You can get all different kinds of sense of social distance that has implications for the expected dynamics of influence. This is just to give you a flavor of the many validations of a measure where we look and you can calculate and measure the distribution of locally sufficient bridges through the graph and show that it basically is directly related to the rate at which complex contagions can cascade on the graph. But what I want to transition to now is, again, some of the broader implications we get for a reframing of networks through this context of socially relevant diffusion dynamics. And what I want to evoke here, just as a kind of heuristic, I know there's many ways of thinking about this, but from the sociology perspective, one of the ways that we tend to be introduced to networks is what I would call something like a static view. So this is like you're given a network picture and you're going to run certain metrics on that network, which capture various global properties. Now, of course, networks themselves change all the time, so new people are added and removed. That's not what I'm talking about here. What I'm talking about, at some point, even in some time slice, you have a picture of a network and you're going to run some measures on it. And so we're familiar with running things like centralities, where that's a property of a given node and graph structure at that point in time. We'll have eigenvector, highest degree. Now, what we walk through in that paper is to show how many of these centrality measures, in fact, all of the canonical ones, in some ways are relying on some synonymy between a single tie relationship and diffusion in terms of influence. So in the case of degree, it's counting the number of single ties that you have. That captures something like the social psychology of someone being more popular than somebody else, which are an influencer position. Between a centrality being the shortest number of these simple paths that go through that node, and so forth. Now, of course, these centrality measures are useful for all kinds of reasons and all kinds of contexts. The problem is, do they actually capture the influence dynamics that are relevant for complex contagions? Now, what I mean by transitioning to a dynamic view of network structure, and again, I'm not talking about networks evolving and changing. That's a relevant form of dynamism. What I'm saying is, even within the context of a fixed network structure, what complex contagions teach us is that there's actually distribution of possible pathways. Because now that I've shown you that a threshold actually changes which structures, or the amount of reinforcement changes which structures matter, now things like the distribution of thresholds, or basically the distribution of social reinforcement requirements, has direct consequences for the pathways. So what starts to happen is you take a fixed network structure and you can actually decompose that into a wide range of possible flow dynamics or pathways, which are actually interacting with whatever threshold distribution you have good reason to expect in that case. Now, what can happen is what we develop in this paper is a measure of complex centrality, which is which nodes are actually most influential in the spread of complex contagions under various theoretical threshold distributions. And the thresholds that you layer on actually impact that. But what I'm going to transition into now is this property, which seems quite foundational that we've figured out, that characterize basically any possible complex path. And it has to do with emergent directedness. But what I want to make is a point where what we're going to start doing is we're going to actually start characterizing properties of the set of possible complex paths. So you're going to take a graph and you're going to look at how thresholds induce different complex paths, and then we're going to start characterizing those possible counterfactual pathways. And this is an important frameshift because often when we think about empirical studies of diffusion, typically we're only observing one particular spreading event in a system. And so that's actually an exceedingly sparse sample of the possible complex pathways that you observe, and lots of specific path dependencies of where it happened to be seeded due to some strategic intervention. And so much of the literature has not evaluated these network features in this possibility space, where I actually think there's, at least in the context of complex contagions. So this is where I think there's a lot to be learned, and we'll develop a method to do that. One of the properties that we figured out in this possibility space is emergent directedness. And so what I mean by that is we're familiar with directedness as something that is a structural feature of the system. So in something like Twitter, it's like some people follow other people but don't follow in return. So there's an asymmetry in who's observing somebody else. Now, there's lots of research that's very interesting and relevant on how things like directedness, directed ties influence the diffusion dynamics that you would observe. What we're going to be doing is running a thought experiment, which I think helps us get closer to something like universal features of this possibility space, which is we're going to start with a system that by assumption has stripped away as much directedness as possible. So what I mean by that is we're going to have nodes where every single tie is undirected, so that influence and information can flow both ways. And nodes have no difference in their persuasive capabilities and anything else at the node level would increase or decrease diffusion. And then what I'm going to show you is that even within this environment, which is arguably the simplest possible network representation, what complex contagions induce is directedness in diffusion dynamics, such that what is entailed is it is a property of complex contagions that they are directed as a regularity. And why I think this is important is because as far as the formal science goes, complex contagions is one of the best theories we have for understanding how culture spreads. So if complex contagions are fundamentally directed in nature, it also teaches us something about the way that culture evolves as a fundamentally directed kind of system. So what we'll do, and I'll walk you through specific examples, but when we iterate through all the possible complex paths, we can start representing hotbed areas where they are more likely to flow. And that's when they're seeded from any possible direction. In fact, across a wide range of possible origin points. So this could be imagining some policy intervention where like we're going to target here, we're going to spread, and we're going to look over possibilities. It could also be some random fluctuation in the system. So it randomly crops up due to some sort of response to some environmental factor, and under some conditions, it happens to catalyze a local event and enable spreading. Both are relevant for cultural evolution. This generalizes across those scenarios. Now, what I'll be showing you is first a deterministic example, because in order to summarize networks along these lines, there's lots of statistics we have to run, but it's to give you some sense that actually on the ground in local environments, this is a fully deterministic observation. So if we take a simple diode graph like this with these communities, red being the contagion, under a simple threshold like 2, we'll see that it diffuses from one and diffuses to the other, easy peasy. So we're going to call that symmetric. But a simple change in the tie here can cause it so that it will only work in one direction. So here's a case where it can spread to the other, but if it happens to start here, no local conditions are satisfied such that any node in the other receiving community is going to be activated through the contagion. This is, once again, I'll remind you, this threshold simplifies it. You get similar dynamics, reinforcement.
Just real quick, so the edge that goes from that green node to the node means that the bridge in the middle on the purple side can't exceed the threshold.
Yeah, so here, each node will actually be exposed to 2 receiving. Here, even though the bridge, in some sense, there's the same number of ties as a function of the distribution, none of the receiving nodes are actually having two exposures satisfied. And what I'm going to argue, actually, is that actually this is what most of the time happens. That this is actually a harder condition to create, which is part of the reason why complex contagions and any amount of randomness, which is, by the way, the generating mechanism for the small worlds, are far more likely to induce this kind of situation. So we develop a causal inference method, and I won't get into all the details. There's lots of fun stuff under the umbrella of causal inference. This is a kind of DAG. I'm happy to talk more about it. But the gist is, the simple intuition is we're just going to run a ton of simulations on a network from many, many different seeding points. And what we do is we basically just ask in any given cascade, was a node involved in a chain of diffusion such that other nodes' adoption was conditional on that node's adoption. And anytime we run a simulation, we're basically going to give a score to that node or that edge. Now, when we iterate and we show robustness to all kinds of things, it turns out to actually, even in really large networks, is we can run this on the order of like 20,000 node networks pretty easily. Actually, you don't need that many, nearly as many samples as you would think, because you'd be right to be like, well, don't the combinatorics explode here? It turns out actually pretty much just whatever n is, whatever that number of samples is, which is often quite reasonable, the margin of error is actually quite low in the sense that if you start running more and more simulations, the ranking of nodes along our measures is actually stable, which is a really nice property. But what we do is we run all these different simulations. We basically score how often nodes and edges appear in these causal chains. And then what we can do is take an undirected network and then start filtering it through a measure of basically node importance and edge importance. And what we started to see right out of the gate is that oftentimes the structures that showed up as most important were not those that we would have expected given existing topological measures. So we defined various measures over this distribution of basically causal importance scores. One is just the normalized importance of the node and edge. But what we can get when we define causal importance as a function of I and j in this sort of conditional probability sense, we can start asking, is the causal importance score from I to j the same as the causal importance score from j to I in the edge? And that's what we then measure as causal flow symmetry at the edge level, but then we can aggregate that over the whole network and basically get a measure of overall how symmetric are the flow dynamics. When I is causally important for J's adoption, is it the same? Or is it often the case that it's more often showing up in cascades flowing in one direction? And again, this is over a space of possible diffusion events, which is agnostic to origin point. So we're going to talk about some results. So first, just to be in conversation with longstanding networks research, we look over a wide range of these small world networks generated in the Watts-Strogatz method. We also look at various empirical network data sets like the Ad Health Network, the Banerjee Village, diffusion of microfinance networks. They have a nice array of network properties. So the first result I'll show you, this is using our causal flow measure, is this consistent pattern we observe where as you increase the threshold for adoption across all these different graphs, you systematically reduce the symmetry of the flow dynamics. And we have a variety of mathematical proofs which provide, I think, pretty simple intuitions for why. Basically, the more that you set a condition on some local configuration, you're basically now requiring that that condition be met on both sides. If it's a simple contagion, by definition, it's always met on both sides. But as you start imposing more and more criteria for what it requires for it to be locally induced, it just decreases the probability that probability is independently satisfied. There's lots of other ways of proving it. Entropy has some nice properties here as well. But this is just the raw statistical results. As you increase the complexity of the contagion, it becomes more and more asymmetric. We show robustness to all different kinds of things, like we look at different diffusion models, like linear threshold model and dependent cascade model. We look at noisy subthreshold activations. So what if at some probability at any time slice, some people who would usually adopt as a complex contagion suddenly can adopt as a simple contagion? Turns out that not only do the asymmetries hold, but that actually induces its own asymmetries, which are arguably more of a methodological artifact than anything else. Asynchronous, synchronous updating, sampling convergence, and seeding method where we do cluster versus random seeding, and we get surprisingly convergent results across all these dynamics. Now I want to get into some of the theoretical implications. So let's revisit that strength of weak ties idea. One of the properties that has been described as sort of special and interesting in small world networks, and this has been championed, for instance, in network neuroscience, so it's generally talked about, is that they achieve some balance of local segregation and global integration. So you get to have your cake and two. Local networks get sort of idiosyncratic and develop their own unique cultures and diversify, and then the long ties allow that to spread and mix in the population. So the conjunction of local clustering and global interaction provides a structural substrate for the coexistence of functional segregation integration. However, what we find is that actually is a characteristic feature of the way that weak ties operate in the structural sense, for complex contagions, is they're directed most of the time. So what that means is that actually, rather than facilitating integration, they're more often giving one small local community more influence over the other. It'll be easier for that area of the network to diffuse into rather than the reverse. And we use tie range to measure the structural weakness of the tie. So we're not talking about like emotional weakness, right? Because we're trying to simplify the structure as much as possible. And what we find is across all these different networks like Watts-Strogatz, Ad Health, and Banerjee, that as you actually look for, even as a function, the longer that the tie is in terms of the amount of social distance that it crosses, the more directed that it becomes. And in general, they are expected to be directed. We also use this as an analysis paradigm when we start characterizing flow dynamics, which regions are generally diffusing into others rather than the reverse. And this is where we uncover evidence of the power of the periphery in complex contagion dynamics. So here's a particular Ad Health network. And what I'm going to do is show you a visualization where it's basically organized along a core periphery. So the nodes that are closer to the center are those with the more degree. Those who are further out have the less degree. Now, the following result is robust to different ways of measuring coreness for what it's worth. But basically what we see is as we increase, so red is the node importance in our causal measure, as we increase the threshold, the distribution of causal impact in terms of like how many complex contagion pathways they're participating in shifts from the core periphery. So the flow dynamics are going into the core rather than from the core out. And this is aggregating that result over the family of networks. And what this actually tracks with is there's a variety of research in sociology. I'd be happy to talk more about this, where plenty of innovations from like technologies to art forms to scientific breakthroughs emerge in the periphery first rather than in the most highly connected core. And people try to theorize that in various ways. We're providing a network dynamic. So insofar as those are expected to be complex contagions, and there's good reasons that they would be, then our analysis suggests that entails a periphery to core flow dynamic. And one idea I'll get into your head, this is a bit blasphemous, but I think it'll be fun. So we're used to thinking about the center or periphery of a network, but often that's sort of talked about as a kind of influence. But when we get into complex contagion world and we're noticing that the periphery has considerably more influence, then like what really is the center of the network when we start thinking about the regions that are driving the diffusion dynamics?
Is it because the periphery has more this structure, like this triangle that you were showing?
That's right. That's right. Yeah, that's exactly right. So oftentimes, like if you think about brokers who bridge different networks, while they have greater diversity of exposures, their connections aren't themselves connected to each other. And in fact, that's definitional of brokerage. The more that they're connected to each other, the less brokerage you have. But that's exactly why they would struggle to spread complex contagions, because of the lack of reinforcement among those different groups. And what you tend to see in the periphery is like lower kurtosis, like more uniformity in the degree distribution. And those are the structures which create sustained reinforcement for the development of complex paths. So in one way, you could think like connected peripheries just basically are one massive complex path. I'm oversimplifying, there's variation. And that's the question is, are those complex paths then emanating out from the core? And oftentimes being in that central position actually has come at the expense of the reinforcement for those complex paths.
My point being that if you start having communities, for example, the links between communities could be also these central points in the network, which are also kind of don't have a lot of diversity of common friends.
Yeah.
So that could be also very important. So the thing that you were saying about central being less important in Contagion only applies if you have no structure or big community structure.
Well, so there's a couple things. I mean, it's an interesting point, but in addition to the topological factors, there's a lot of evidence that the more central actors also have a greater psychological obstacle to diffusing complex contagions. So if a contagion is complex because it's innovative or it's like, say politically controversial, these sorts of things, the more observed you are and visible in the network across a greater diversity of actors, the greater risk there is of social sanctioning or disagreement across those viewpoints if you start doing something innovative and different. What the periphery can benefit from is a lot of mutuality in terms of people, high trust relations, and also shared alignment in their viewpoints, there is a kind of puzzle here, because in some ways, if you could get the central nodes to spread the complex contagions, there are many ways in which they are in the right position to innovate, because they are the brokers that are exposed to a greater diversity of viewpoints. So in a recombination sense, they're going to have more opportunities for innovation in that sense. But in terms of complex contagions that require high trust and overcoming social risk and avoiding sanctioning, they're often in the least advantageous position for spreading complex contagions. Now, none of this is hard and fast. There's lots of other factors that contribute, but I think you've made some helpful points on that. And as a final analysis, I want to talk about the implications of bridge formation. So as we think about networks changing over time, just as you were saying, we're going to see that when new ties are forming in sort of what's called triadic closure, maintaining that local connectivity, those are going to be more conducive to symmetrical bridges. But that's actually a constraint that we have to impose. So we think about this because often in organizations, we have to build bridges as networks grow. So this can be like in the case of a merger, you have to build network structures between different firms and teams. And we'd often do this to facilitate knowledge transfer as well. Now, often the objectives vary in whether the diffusion you want is asymmetric, so knowledge from one group to the other, versus integration, which is more of the symmetric. And when we look at bridges forming both in the wild but also at organizations, they happen through a variety of like quasi-random or intentional processes. My favorite example of a random one is like you set up an informal social function and a group of people happen to share a cab or an Uber, and there's a nice study of this that like actually network connections and organizations and the informal networks in particular form through these endogenous random events. But little to no network research has been done on these network building practices in organizations, certainly along these asymmetric, symmetric lines. So we believe we have some formalisms to help here. So what we're going to simulate is take these two different communities and we're going to form bridges at random between them. So one is just through pure random sampling. The other is randomness, but we're going to add a factor for triadic closure, which is the probability that a new tie added is actually going to close a tie. And what we see is that in this particular example, it generalizes. But if you're in the upper half, you're in a symmetric bridge, so it can flow in both directions. If you're in the bottom half, you're in an asymmetric bridge. What we see is, just in general, if we're in the purely random regime, you actually have to build bridges that are surprisingly large in order for them to eventually become symmetric. Because it's worth noting, right, in the limit, a maximally connected network, or a fully connected homogeneously mixing network, is symmetric. So in some ways, just adding ties will get you to symmetry, but you have to build really quite large bridges. In this case, the communities are not that big in order to induce symmetry. Most of the time, what you would expect through randomness, the bridge that's going to form is asymmetric, which follows from the analyses we did of the weak ties. But if you increase the rate of triadic closure, so the probability that that new tie being added is actually going to close a triangle, you can systematically increase the rate at which that bridge is going to be symmetric. And this is interesting not only from a strategic point of view, but lots of cultural factors actually mediate the rate of triadic closure. So there was a recent analysis of triadic closure on Twitter, which of course in this case was US-centric, and it showed the rate of triadic closure was really quite low, like 12%. But there's arguments spanning anthropology and psychology and otherwise that cultures vary in the rate at which they require or pressure towards triadic closure. So you can think about more collectivist cultures where a lot of social networks are built around families, and there's a high risk if you bring some sort of outsider as like a new friend or a new romantic partner. And instead, they actually require a lot of shared contacts and information to maintain the stability. So that would be a culture that has greater rate of triadic closure, whereas more individualist cultures where there's a lot more autonomy to the individual's level to shop around and go to different communities and spontaneously make ties and bring random friends to a party, that's the kind of cultural dynamic of tie formation that you would expect to induce asymmetric bridges. So one of the things we're thinking about more generally is the way in which these tie formation dynamics can actually give predictions for whether certain kinds of cultures are more likely to have asymmetric or symmetric diffusion dynamics, which we think will be a fun and cool and useful way to think about cultural dynamics and networks. So I want to finish with a quick note on diffusion controllability, because one of the things that follows from this actually is if you were to try to architect a very specific diffusion dynamic, directedness gives you the tools. Like here you can imagine like a kind of network switch in the diffusion of dynamics. What I want to show you is a visual example of just how good we've been able to get at this. So this is a fun little parlor trick my postdoc Fabian developed. So we're going to hold the network constant. It's highly dense, but like there's a lot of far-ranging ties. And this is the same network, simple contagion. We're going to see how that spreads. And we see that it just cascades randomly across the whole network when randomly seeded. So we're going to keep the seeding the same, everything the same. All we're going to do is change the threshold. And this is what the diffusion dynamic looks like. Yeah. So to say that in simulations, we've been able to achieve quite arbitrary levels of control through that. So directed flow emerges naturally when contagions require reinforcement. We developed this causal inference method to pick up on that. Strength of weak ties appears in often cases for complex contagions to be directed. The periphery can achieve surprising amounts of influence over the core for complex contagions. And these flow dynamics are not just fuzzy statistical aggregates. We can actually use them to control diffusion dynamics in these simulations. So thanks so much for listening. Please get in touch if you want to learn more. And I really look forward to your questions.
Thank you so much for sharing this with us. As the dynamics change over time in complex contagion reviews, is there a point where the complexity threshold declines because it becomes such a widespread norm, or just a group like this that the tipping point? Do you see any acceleration of declining complex social?
Yeah, so it's a very interesting question. One way to think about that, just as a formalism, right, is what if agents updated their thresholds over time? So we as a simplification. So absolutely they do, but that also introduces a can of worms, right? You can imagine some cases if seeing that something is more popular, like you're suggesting, means it's more advantageous to adopt, you could imagine an interaction with popularity. But the reality is a lot of these contagions are interacting in some ecology of contagions. So as a contagion spreads and it becomes more observable and recognized, people also start sharing information about the contagion and stories about that. And sometimes if it becomes more associated with particular social groups, other dynamics induce, we're now being adopting this contagion now associates you with that particular group. And so there's a lot of very interesting non-trivial dynamics that could actually increase thresholds rather than decrease thresholds. And a part of that is due to the endogeneity of a lot of these processes and our awareness of them. But that's a direction I'm very interested in exploring.
In the endowment of the node, but the same thing continues to change that we set them. Is that a variable you would put on the node level?
If I were to a simple way to start simulating this is you could just have various updating functions or even noise. And we have had it so that there's fluctuations, agents, you can imagine like good day or bad day level, like mood fluctuations. When they go up and down, that kind of simple fluctuation doesn't change any of these dynamics. You'd have to start assuming particular kinds of fluctuations. And now you're in the scenario of trying to characterize particular paradigms, which could be interesting, right? Like maybe you're going to look at the sort of, what's the sort of Santa Fe bar problem, right? Yeah, so there's like diminishing, like there's a certain moment where there's enough people you want to go because it's cool, but then now when it's crowded, you don't want to go anymore. So you can imagine updating functions that capture that scenario well, but I think there's going to be lots of different paradigms, some of which, like, say the more popular something gets, the more politicized it becomes. I wouldn't expect this straightforward sort of reduction of thresholds. You could actually imagine lots of cases where the more politicized it becomes, various groups actually increase their threshold of adoption.
Yeah, this is super interesting. So
Thank you.
I'm still formulating this question, so this might not be totally right, but I'm curious about like how potentially different kinds of complex conditions like interact.
Yeah.
Looking about it in the context of culture.
Yeah.
That's not like we're a passive vessel by whatever things through. Everybody wants to change culture today, like real. But like to the extent that this is happening in an environment where there's different multiple kind of pressures or factors trying to make something contagious. Like when you're focusing the same kind of settings, or it is what ends up becoming more contagious as the property over things or yeah, there's like a series of questions there about it.
Yeah, absolutely. So in my view, this is one of the most exciting areas of research for contagion dynamics is these interacting contagions. My intuition is that the formalisms we develop are going to be very helpful for understanding that, in part because like if certain social groups are associated with particular contagions or you're trying to all sort of vie for some sort of global influence, we can then characterize their sort of whether they are in an advantageous position or not in that. And we could even start anticipating through the expected directedness, like where are the battlegrounds going to be? Where are contagions from group A and group B going to interact and intermix? And then something I'm also interested in exploring in that context are associative dynamics. So as we start interacting different contagions like music styles with clothing styles, how do they actually have certain semantic spillovers that can be catalytic or actually interfering with that? And my postdoc Fabian and I, he's been leading this really interesting project, for example, where we're using some of this to understand the spread of conspiracy theories online. And one of the things we've observed in that is there's an interaction between both the social network structure and the semantic network, where conspiracy theories are actually interacting and shaping their interpretations of each other. And people's previous history of encountering and adopting different conspiracy theories actually, this is also related to threshold updating. It can actually impact their threshold for the adoption of subsequent conspiracy theories. So we're just at the start of that, but it's a very exciting project where implicit in it is a kind of ecology of contagions.
Sorry. So when you reference, that the thing you postdoc are doing as well as other models we use, such as my uncle's paper, are you saying that like a lot of these complex contagions arise from not a single agent spreading connections, but more like multiple agents, like bridging some like tangential gaps between one another?
To some extent, yeah. So one of the things that came out of the complex centrality measure is, in some ways, you have to think of influence at the group level, right? So some of you are probably familiar with hypergraph level stuff. There are some interesting connections with that. There are some gaps, but the gist is that we're used to thinking about influence at a node level. I think that, as useful as that is, I think that's largely a spillover of a social psychology of how we actually think of the semantics of influence. But in complex contagions, we often have to think about the influence of regions and groups. Yeah.
I'm curious about one of the assumptions that you made this model is that at the fundamental level, all the nodes are net, all the ties are net.
Yeah.
It seems like for real social networks, one of the things that informs the structure of the network in the first place is the properties.
Yeah.
So people end up with more connections precisely because they're more persuasive and more friendly. There's one causal direction that properties of the nodes and structure. Everybody else is doing the opposite way, it's taking structure properties.
Mm-hmm.
So I'm curious especially for networks that are going to be more realistic, you find yourself getting back out of the properties that inform the structure of the network in the first place, or something different?
That's a great question. There are two different questions there. I'll get to the one around network updating. But the first one is that from what we can tell, as soon as you add more of that real world information, it just adds more reasons for asymmetry and other factors to use to understand why, like what the asymmetries would be. So if you think about something like, so we're talking about emergent directedness. We use emergent because it comes from the interaction between the threshold distribution and the topology, which is always going to be there as a layer. But then if you add something like node level variation, that's also going to induce symmetries, and it's going to interact with these other things, because if two nodes are connected, but one is more charismatic, there's going to be ways in which they'll give more information influence to the other rather than the reverse. Now, there's lots of, like I was alluding to before, like tons of highly endogenous dynamics where none of that's like uniform. So it's not like being more central and charismatic is always advantageous, because you can run into all kinds of trouble. You have many, many more stakeholders to manage. Suddenly you're responsible for venture capital in the order of hundreds of millions of dollars, and things start restricting your freedom in terms of your ability to communicate yourself. So there's lots of really subtle dynamics like that. That's interesting. There's so much more to say about network updating, but what I want to just seed as an idea that's interesting is, one open question is, let's say you were to have more information about who's influential in terms of complex contagions, because the previous way of detecting influence fits with our psychology, because without network math, which is a relatively modern invention, you could just look at people and develop judgments for who is or who is not influential, right? And that could create a preferential attachment like you're describing, right? But what would it look like to have preferential attachment for something like influence in complex contagions? Does that happen to some extent? Are some people perceptive of it, like maybe noticing an influential community in the workplace, and people like being like the in crowd of something, in the crowd? That's where we start getting the hypergraph stuff. And or if we start increasing the ability to detect this stuff, what are the dynamics that emerge? Like, you actually could get into scenarios where if you increase preferential attachment for those who achieve a kind of centrality in complex contagions, you then defeat the structural advantage they have as more people flock to them in terms of maintaining the sort of influence that the periphery has over the core. So some of that position of the periphery in some ways involves not being too visible. And that's where there's a lot of sociological theory also about this, of like the need to protect innovators. Because if people who are innovating are made too visible too early on, too central, then they can actually prematurely halt an innovation process, get co-opted, and these sorts of things. Yeah.
Can I ask another? Go for it.
Sure.
So a lot of viruses make the contagion models like this a positive state and like a neutral, negative state. You don't have it. But what if it's like there's two possible on states, you're a Democrat or you're a Republican.
Mhm.
So in the U.S. politics, 50% is Republican, 50% Democrat. Directedness for Republican, turning on more Republicans, one directed and a cascading effect, but turning them into Democrats, another cascading directed effect. And so overall, it's not necessarily directed because there's two possible, positions you can be in.
Yeah, like I said, I think all these things we started from the position of minimal realism, but the reason why is because if you literally can't escape directedness at that point, it's then the burden is on someone to explain how adding more and more complexity and variation of different kinds would somehow reverse this fundamental directedness. So that's sort of the logical approach we're taking. So there's lots to think about the subtleties of these dynamics. But I will say there's this really cool paper in Nature a couple of years ago. David Rand's on the paper, and there's some others where they look at assortativity between Republicans and Democrats in influence networks. And in the title is something like undemocratic to say, oh yeah, it's information gerrymandering and undemocratic decisions. And what they find, they didn't have the network math or theory at the time, but they observed that due to how the distribution of Republicans and Democrats were, even if you held the number of connections each of them had constant, through a kind of gerrymandering, you could give one party more influence over the other. So even if the voting procedure was ostensibly fair in the aggregation and there's equal numbers of Republicans and Democrats, just through the sheer distribution of ties, you could give some an advantage over others. And so our theory would provide a framework for analyzing that directedness through the lens of complex contagion. Yeah.
I have a question. Yeah. Complex vaccination?
Yeah.
Good?
With enough money. No.
Struck by the little person on that side that wrote out.
Yeah.
Like his wave metaphors are quite visually coherent.
Yeah.
But then if I said that I know that these nodes are in line for this wave of directedness.
Yeah.
Would vaccination just give those people way more friends, or give them way more information? Because some of them have new links, and that might pull them out of this.
Yeah.
Of this connectedness.
Yeah. So in Damon's book Change, he talks about this really powerful example of seeding a change in agricultural technology in Malawi, where they were at risk of global famine in the country. And it was like code red level risk. And they identified that their agricultural activities were really drastically underperforming under the current drought conditions. And there was actually a really cheap and efficient solution called pit planting. Like there was no reason, like all of them had everything they would need to implement it. And the government threw money at them, threw incentives, did all kinds of mass messaging, and it basically didn't budge for years. And the risk of famine was increasing. And the researchers used complex contagion theory to strategize the seeding of the pit planting by recruiting small groups of people in local neighborhoods to work as teams. And they were able to, through the complex contagion strategy, basically achieve a cascade of the adoption of this pit planting technology. So our tools just give more to work with in terms of who is actually in an advantageous position to accelerate the spread of that. And maybe there are also cases where almost like in rumor diffusion, it would be beneficial for certain groups not to encounter the contagion for a period of time, like say there's a risk of politicization or something. So there's always a trade-off between like just accelerating the spread to the greatest number of people as fast as possible, because sometimes actually you want to limit the rate of diffusion to build momentum like in the periphery and critical mass. So this gives some lever points for that, but I do doubt the limits of total control, because we're in a world where we have all the information we need for all the nodes and networks. And as you know, like real world networks are changing constantly, and there's tons of measurement error and these sorts of things. So I don't want to oversell the level of control that's possible in that setting.
Another question, guys?
Yeah, I have a question. I found fascinating that by implementing a process which is called Contagion, the network becomes directed.
Yeah.
Immediately. This is not directed, but it's a process that makes. or the influence of nodes.
Yeah.
There's another thing that makes it connected, which is temporal dynamics. The fact that links are not activated, they are not always there.
Yeah.
So has anybody combined the two of them?
No, this is.
The other,
I mean, lots of people have studied temporal networks, but that's the kind of thing that we're super interested in as another. And there is some evidence, generally in the literature on like homophily, there's lots of cultural factors that increase the likelihood of ties forming. So if you invite me to a social gathering and I make friends with one of your friends and we close a triangle, then over time, I'll have more reasons, like I'll get invited more, we'll start interacting, suddenly you're influencing me, showing me music groups, doing other things. And so you can like increase the similarity of people over time. And so in a way, what's happening is the contagions are actually shaping the network, right? Like if, a given musical concert is becoming contagious as something that's interesting, people then go to it and networks form ties start forming at the event, right? So I just think a really interesting reason why you would want to study that is to study this sort of chicken or egg reciprocal dynamic, but the contagions shape the network and the networks shape the contagions.